Hello everyone, today we are continuing our Data and Statistics unit with section 3 covering visual displays and problem solving. So we are going to go ahead and start with some examples looking at histograms, then box and whisker plots, then we're going to look at a stem and leaf plot, and then we're going to look at a dot plot before we do some problem solving. So starting with the histogram, and you'll notice I actually have this data set here. This is height in inches. This is some heights of students in one of my classes, and we already have them in order here, so we go from 64 to 76. It would be good if you went ahead and wrote this down because we'll be using this data set for all of our visual display examples in our notes. So starting with the histogram, we have in red here, the histogram is best for displaying frequency and it categorizes your data. So this is a good quick glance at all of your data as far as frequency goes, and then if you're looking to categorize it, this is also the type of visual display that you're looking for. In order to create a histogram, you have to categorize your data into a few sections. And I already divided this out, so we're going to have this many bars in our histogram, and we need to figure out how many data points fit in each of these categories. Now the categories, I created them by looking at our data, and I knew that I was looking for something that would have 2 to 3 data points in every section, and they need to be connected, and they should, because the difference between a histogram and a bar graph is that histograms, the bars are connected, so where you leave off should be where you start for the next category. So I have 64 to 65, 66 to 67. If you wanted to have less bars, then you could do 64 to 67, 68 to 71, 72 to 75, and then 76, and then you'd go a little past here. So let's go ahead and mark our frequency for our data points here. So I have 64 and 65, so there's 2 data points that fit in that first category. 66 and 67, there's 1, 2, 3, 4 data points that fit in that category. 68 to 69, 1, 2, 3, 4, 5 data points in that category. 70 to 71, there's 2 data points. 72 to 73, 1, 2, 3. 74 to 75, 1, 2, 3, 4. 76 to 71, there's 1 data point. So now that we have a frequency, the number of times this category occurs in our data, we can take that and we can plot it on our histogram. And that's what we're going to do to the side here. So I already drew a lot of this graph here. So I have the number of people on the side, and I have height in inches along the bottom. And I already drew where my categories are going to be as well. I have 64 to 65, 66 to 67, 68 to 69, 70 to 71, 72 to 73, 74 to 75, and 76 to 77. So we need to, first off, give this a name, and we also need to draw in our bars. So we're looking at the number of people and height in inches, so a good name for this histogram, let's just call it exactly what it is. This is student heights. Alright, so now that we have our title, we're going to go ahead and we're going to draw our bars. I have 2 64 to 65, so I need to go up to 2 in this bar. When I start my next bar at 66, I'm going to make sure that it's sharing this side. So I have 4 for 66 to 67, so I'm going to continue that line up to 4. I'm going to carry it over and bring it down. Then 68 to 69 is at 5, so we're going to go up to 5, over and down. So we're making sure that we are connecting our sides once again. And your histogram, just a reminder, has to connect. That's what makes it a histogram. Then 70 to 71. 70 to 71 is shorter, but we still have to share this side. So I'm going to come to about here, and that's where I'm going to draw my bar from. So I go from 2, 72 to 73 goes back up, so we're going up to 3. 74 to 75 is 4, so we're going up again. And 76 to 77 is 1, so I start at about 1, draw over, and there is my histogram altogether. So next we have the box and whisker plot, and here box and whisker plots, or a box plot, is best for displaying your 5-number summary. Just a reminder, your 5-number summary would be your minimum, Q1, your median, Q3, and your maximum. And box and whisker plots are good for independent data that is related. For example, test scores. So we are looking at specifically heights in this scenario. That's another example. It's single data that belongs to a group of people, and it doesn't matter who those people are or what number goes with which person. You're just looking at the numbers as a whole. So I actually already calculated the 5-number summary. You should go ahead and write this down. For our minimum, we have 64. Our Q1 is 67. Our median is 69. Our Q3 is 73.5. And our maximum is 76. So in order to draw a box and whisker plot, you first have to calculate all that, and then you're going to need a number line. So I drew my number line out already as well, and I'm going from 63 to 77, and I'm choosing to make my number line that length because I need something that is past our minimum data point of 64, and I need something that is past our maximum data point of 76. So it makes sense to just go one more tick mark. The other thing I want to mention here is I went up at a scale of 1, 70, 71, 72, 73. You don't have to, but it's going to depend on your data. In this situation, my data is it doesn't have a super wide spread. My range is not very large. And because of that, then it makes sense to go up by 1 every time. But if we had a data set that was ranging from like 0 to 100, that is way too long for your box and whisker plot to have a scale of 1. So then you would need to change that, and you would have to do your best you can to make your numbers lie on an accurate position. So starting with our box part, it's called a box and whisker plot because it has a general shape like this. So you have your box on the inside, and then you have whiskers sticking out to the edges. We are going to start with the box part. The box is made up of the very far edge is Q1, the other far edge is Q3, and then the line that goes in the middle is your median. So I'm going to start with my Q1 at 67. 67 is about here, so I'm going to go above the line, and I'm going to put a point for now. So this is going to help me draw my box. So I'm just drawing a point above 67. Then my Q3 is at 73.5, which is halfway between 73 and 74. I'm going to do the same thing. I'm going to go right above it and draw a dot. And that is where my box needs to connect. So from there, I'm going to draw a rectangle connecting those 2 points. And now I'm going to put my median, which is at 69. So you can put another dot there, but you really just need to draw a line right where 69 is in our box. So this is your box part. Now we have to draw our whiskers. To get your whisker, you're going to put a point at both your minimum and your maximum. My minimum is at 64, so I need a point right about here. And my maximum is at 76, so I need a point right about here. Now I have all pieces of my 5-number summary. The only thing that's left to do is to connect these points to our box. So I'm just going to draw a line from my point, my maximum, to this box, just a straight line. And I'm going to do the same thing from my minimum to the box. And that is your box and whisker plot. This is something that I actually really like to look at when I'm looking at things like your test scores, because it tells me right away that our middle number is over here, and it gives you a visual picture of how far out your higher scores are compared to where the rest of your data might be. So this is half your data over here, and the other half of your data is down here. This is telling me that I have mostly larger numbers in my data. All right, we're going to go ahead and take a look at stem and leaf plots. If you don't already have your data written in a place where it's easy to see, I recommend writing your data points down again so that you have a quick reference. All right, stem and leaf plots are best for quickly displaying frequency. So histograms still display frequency, but it gives you more of a visual picture. A stem and leaf plot is going to give you that visual picture with more of the numerical data. You're looking at the numbers themselves. So to start with our stem and leaf plot, I'm going to take the number 64, which is part of our data, as an example. So the number 64 would go into our stem and leaf plot like this, where 6 is your stem and your leaf is 4. So this is from our tens place and this is from our ones place. I read this as 60 and 4, so 64. Then our next number in our data set is 65. So the 6 stays the same because it has the same stem. We're still in 60. But now our leaf, instead of 4, is 5. So I have 64, 65. And you don't put any commas in between our numbers. This is just two separate data points, 64, 65. And this continues like so. In order to know that we are looking at 64 instead of something like 6.4 or 604, something like that, we know by creating a key. So my stem and leaf plot, I'm going to put my key down below. So my key says that 6 in my stem column and 4 in my leaf column, 6 and 4, is equal to 64. That tells me that these are numbers from your tens place and these are numbers from your ones place. If you had something like, let's just say you did have 110, then your stem, since we're keeping this as the tens place, you would put 11 and your ones would still be in the leaf. All right, let's continue with our data. So I have 64, 65, I have 66, 66, 67, 67, and notice I have two 66s, so I write the 66 in again. You don't just put it in once, you put it in for every time that number occurs. Let's see, 67 and 67 is where I left off, so I have 68, 68, I have 69, 69, 69, and then I go into the 70s, so I have a new stem, we're in 70, and I have 7D, so that means there's nothing in my ones place, so a 0 is what my leaf is. Then I have 71, I have 72 twice, so there's 2 of those, 73, 74 3 times, and 75, and 76. And that is my stem and leaf plot. Last but not least, we have the dot plot. The dot plot is best with small data sets because you have to plot each point as a dot on a number line. With our data set, we have just enough that a dot plot is a good representation. So we're going to take these, and I have a number at 64, and I'm going to go to 64 on the number line, and I'm going to put a dot right above 64. Then I have 65, so I do the same thing above 65. Then, this is where things get a little different. We have 66, and there's 2 of them. So you still are going to put a dot above, but you put a dot above for every data point you have that fits into that category. So because I have 2 of them, I first put my singular dot, but then I have to stack another one on top of it. So it looks like that. And the more data points you have that have the same number, the taller your column will be. All right, so now I have 67 twice, so I need 2 for that one. I have 68 twice as well. Then I have 69 3 times, so now I need 3 dots stacked on top of each other. Then I have 70, I have 1 at 71, I have 2 at 72, I have 1 at 73, I have 1 at Nope, I have 3 at 74. I have 1 at 75, and I have 1 at 76. And notice again, I purposely made my number line so that I have a data, my next tick mark past my data, and my next tick mark past my data on the other side as well. This is your total dot plot, and I'm actually just remembering that I forgot to put a title on the box and whisker plot and the stem and leaf plot, but I'll remember for this. The title will be the same as we used with the histogram, and it just goes above it again. So I have student height. And I will go ahead and put that on my other plots as well, so if you're looking at the notes keys, the title will be there. Those are my visual displays. Now that we've created our visual displays and talked about when they're best suited, we're going to go ahead and do some problem solving. So let's go ahead and change the page, and here we have this first question about a histogram. And I already wrote in a couple things here, and I'll explain what that is in a second. So the histogram below shows the number of hours worked last week by 40 employees at a restaurant. Notice that's 40 employees. All right, so when we look at our histogram, the types of questions that were being asked, it will be helpful to know not how many are in each individual column, but how many are behind that as we go. So because I have 40 total workers, my last bar should have a 40 on it, because every data point below in this column and below should equal to 40, because there's a total of 40 people who took our survey. So in our first column we had 6 people, then we added 17 more, so we're at 23. Then we added 9 more, so we have 32 total people so far. Then we add 5 more to make 37. Then we add 1 more to make 38, and then 2 more so that we have a total of 40, which is what we wanted. So looking at our first question, letter A, says give an estimate, a range, for the median of the data set. So there's a trick we can do here. You could try to figure out where the middle would fall in here, which you might be able to do just looking at the graph. I'm going to talk about what if it's kind of confusing, what if it's hard to tell. That's where those numbers at the top is going to come in handy. In our formula to find an estimate for the median, this is going to tell you your location, not your actual median. We can find our location by taking the number of data points, adding 1, and dividing by 2. So if I do 40 for the median estimate, I'm going to take my total number of 40, I'm going to add 1, and then I divide that by 2. And that gives me 41 divided by 2, which is equal to 20.5. So our median will be exactly in between so there will be 20 data points on the left of the median and 20 data points on the right of the median. And so we're looking for halfway between those 2 center data points. So we are at 20.5, so between our 20th person and our 21st person is where our median will be. Again, that's the location of the median, not the actual median. So if we go to our histogram and we're looking for where the 20th and the 21st person are, 6 of them were already used. In this column, we hit the 23rd person that we surveyed. So the 20th person and the 21st person are going to be in this column, which means that my estimate for the median has to be between 20 and 30 hours worked, because our median will be in that column. So my estimate is 20 to 30 hours worked. Letter B, is the mean more likely to be higher or lower than the median? In order to calculate where the mean is, we're not actually going to calculate the mean, and we don't need an exact median either. But we do know that the median has to be in this column, and our mean is our average. If we have a lot of our numbers that are being pulled to the right as opposed to pulled to the left, your mean, your average, is going to pull with it. So if we look at this data here, we have 23 people that have worked somewhere between 10 and 30 hours, and then the rest of our data set is going to be above that. Some of them even working 60 to 70 hours. So you're looking for, on average, how many hours were worked. And based on the fact that these numbers are quite a bit higher, and they're going to pull our data points, they're going to pull our mean just a little bit further this way, my estimate is that the mean will actually be higher than the median, because the median is for sure in this column. But if our people that are in this column all worked, let's just say they all worked 30 hours exactly, or 29 hours, they're gonna pull the data more this way, so that would help too. So it's a little bit, it is an estimate. We don't know exactly. If we were to calculate, if we had the exact number of hours they worked and we calculated it, we could figure that out exactly. But we're looking at the graph. I'm recognizing that a little under half of our data is all on this side, but it's quite a bit higher. So I'm guessing that my mean is probably actually going to be in the same column or in this column here with the 30 to 40 hours work. So I'm going to say the mean is likely higher than the median. Then letter C says give some possible values for the interquartile range. In order to give some possible values for the interquartile range, I have to have a possible value for Q1 and a possible value for Q3. So I can actually do the same type of thing with my estimate that I did for the median. So I'm going to start with Q1. Q1 is the median of the lower half of the data. So if I know that my median is at 20.5 and I don't use the median when I'm calculating my Q1, then that means that I have exactly 20 data points below my median. So I'm going to do the same type of formula. So I have 20 data points below plus 1 divided by 2 is equal to 10.5. So my first quartile is between person 10 and person 11, which means that my Q1, it will be where the 10th and 11th person are, which is in the same column. So we're in the 20 to 30 hours worked. And my Q3, so I don't have to do that same calculation. I just have to take this number and I have to add it to my 20th data point. So I have 20 plus 10.5 is equal to 30.5. So I'm in between person 30 and person 31. And person 30 has to be beyond this bar because person 23 finished this bar. And person 32 finishes this column. So both person 30 and person 31 will be in this bar. So Q3 is going to be equal to 30 to 40 hours worked. So my possible interquartile range, we have to do some subtraction, and because these are a range in of themselves, I'm actually going to be doing more than one piece of subtraction. So I'm going to start with my outermost data points. So I have 40 and 20. 40 minus 20 is equal to 20. And that is my maximum distance. And my minimum distance would be if they had exactly the same. And what I'm just realizing here, something that I missed, and we'll fix this now. We have 10 to 20, 20 to 30. If I have 20, then I would count that in this. So this is really more like 10 to 19, and this is more like 20 to 29. So it might be better to say 20 to 29 hours. And for our range here, and I'm going to fix it on this one. I'll leave it for the other one. But we have 20 to 29, and 30 to 39 is more of what we're looking for on that one. So we'd be doing 39 minus 20, which gives me 19, and then the other subtraction you do is with these two pieces. So I have 30 and 29, which is a difference of 1. So my interquartile range as a possible value could be anywhere from 1 to 19. And the reason why it's a range and could be 1 or 19 is because what if all of our data points in this column were 29? And what if all of our data points in this column were 30? Well, then the difference is only 1. But if all of the data points in this column were 20 and all of the data points in this column were 39, then the difference is 19. So it just depends on what those numbers are, but we have to estimate it that way because we don't know what the numbers actually are. We just know that they're in this category. Number 2 says the average of 1, 2, 5, 9, and x is 4, and the average of 2, 3, and y is 6. What is the value of x plus y? In order to calculate that, you first have to find x and y. So if I know that the average of 1, 2, 5, 9, and x is equal to 4, and there's 1, 2, 3, 4, 5 data points there, this is my formula to solve for x. I add my data points together, I divide by the number of data points there are, and that's equal to my average. So really I have 9 plus 5 is 14, plus 2 is 16, plus 1 is 17. So I have 17 plus x is equal to, and I'm going to start by dividing or multiplying the 5 out too. So I have 17 plus x is equal to 20. Subtract 17, that gives me x is equal to 3. And now I have to do the same thing for y. So I have 2, 3, and y. 2 plus 3 plus y, there's 3 data points there, divided by 3 is equal to my average of 6. I'm going to start by multiplying 3 out on both sides, and then 3 plus 2 is 5, so I have 5 plus y is equal to 18. Subtract 5 from both sides, y is equal to 13. Then, to answer my full question, it says what is the value of x plus y? So I have x plus y is equal to 3 plus 13, because this is my x and that's my y, which means that x plus y is really equal to 16, and that is my final answer. Number 3, the average of a set of 7 numbers is 8. When an 8th number is added to the set, the average of the 8 numbers is now 10. What number was added to the set? So in order to calculate this, you have to set that average back up, the mean. So 7 numbers added together is 8, or the average of 7 numbers is 8. So you have something divided by 7 is equal to 8. And we know that we added an 8th number, so this is our sum. Our sum of the 7 numbers is x. That divided by 7 is equal to 8. Then we took our data set, our 7 numbers, we added an 8th number, which I'm going to call y, and now we're dividing by 8 because there's 8 numbers, and that average is 10. So we're missing the sum of all the numbers, and when we have that sum, then we can use that to solve for our missing piece. So 7 times 8 will give me the sum of all of my numbers, of my 7 numbers. So if I multiply that, 7 times 8 is 56, so x is equal to 56. So this formula is actually, instead of x plus y, it's 56 plus our unknown number divided by 8 is equal to 10. So I'm going to multiply both sides by 8. That gives me 56 plus y is equal to 80. I'm going to subtract 56 from both sides. That gives me y is equal to 24. And that is my answer, because that's the number that was added to the set, and that's what I was trying to find. Alright, we have a few more examples to look at on the next page here. Number 4 says 2 classes were given a math test. The first class had 25 students and the average test score was 86%. The second class had 15 students and their average score was 94%. If the teacher combined the test scores of both classes, what is the average of both classes together? So in order to do that, you have to do a little unsolving before you can actually solve for a new average. So I have some number as my sum of all the test scores divided by the 25 students in the class is equal to that 86%. And then the same thing happens in the other class where you have some number divided by the 15 students gave me a class average of 94%. And you can leave that as a whole number when you're calculating. You just have to make sure that when you find your full answer that you're remembering that it is a percentage, not a score. So we have 25 times 86 will give us our sum of the test scores in our first class. So we're going to multiply that out. And then that means that x is equal to 2,150. And then my y, I'm going to multiply both sides by 15. So essentially we're doing 94 times 15, and that's going to give me 1,410. And now I'm going to take those two numbers and I'm going to add them together. So I have 2,150 plus 1,410. And that is my total test scores for all of most students. And then I'm going to take the total number of students and put it on the bottom, which is 25 from one class plus the 15 from the other class. And when you calculate that out, that gives me 89%. So the total average for all of the classes, for both classes, is 89%. Number 5, in the list of numbers 6x, 10, 20, 7, 13, and 15, the median is 10. Which of the following could not be the value of x? So we're trying to figure out the median. The first thing that you're going to want to do is make sure that these numbers are in order without x, and we'll figure out where x could or could not be. So I have 2, 6, 7, 10, 13, 15, and then we have x that needs to go in there somewhere, and it says that the median is 10. That means that 10 has to be the middle number. If 10 is going to be the middle number, there needs to be 3 data points on the right of it, because there's 3 on the left. So we need a number that is bigger than 10 in order to make it work. So in our options, 21 is bigger, so that would make 10 the median. 14 is bigger, also would make 10 the median, but 4 is smaller, and 4 would mean that 10 is no longer in the middle. So this is asking for which one is not the value, which means that our answer is C, number 4. Question 6 says the average, median, and mode are calculated for the following list of numbers: 3, 3, 7, 10, 12. If the number 1 is added to the list, which of the following could change? The mean, the median, or the mode? If we add the number 1, let's just add that in our data set up here. And before we include the 1, let's think about the median. The middle of this list of numbers is exactly 7. But when I add this 1, the middle is no longer 7 because now there's 3 values to the left and 2 values to the right. So our median would have to go over so that there's 3 values on either side. So our median is now halfway between 3 and 7. So our median did in fact change. So that's one thing that could change. When we add 1, does the mode change? Well, the mode before was 3 because there were 2 values of 3 and no other repeated numbers. When you add 1, that does not change, so the mode stays the same. Next we have the mean. In order to figure that out, we actually do have to calculate that. So I have 3 plus 3 plus 7 plus 10 plus 12, all divided by 5. And when we calculate that out, that gives me 35 divided by 5, which is 7. And if we were to add 1 to that, you would end up with 35 plus 1 divided by 8, which is 36 divided by 8, and that is 4.5, so the mean did change. So the mean also changes. So there are 2 correct answers to this one. Both the mean and the median changed. question 7, which says, which of the following distributions has the largest standard deviation? So remember that standard deviation means that you're calculating the difference from each data point to the mean. So we are looking for data that is going to be spread out really far away from the mean, and that is going to have the largest standard deviation because there's the greatest difference in data points. So if I look at this, A is definitely out because those data points are all really close together. D, I think, is also out because those data points are also pretty close together. So that leaves us with B and C. And as I'm looking at this, the spread from C is not all that far. It only covers 4 of these sections, but B covers the entire 5 sections. So I think B is going to have the largest standard deviation because the data is spread out furthest. This is going to conclude our section 3 covering visual displays and problem solving. We'll pick back up in section 4 where we will learn a little bit more about some of the impacts that changes to our data sets can have.